Good morning, students. Today we'll discuss about the minimization of finite automata. This minimization of finite automata. Minimization of finite automata. So, in this, the main objective in minimization of finite automata is, we are going to reduce the number of states in a finite automata, in a deterministic finite automata, without changing the working procedure. Okay, here it is a transition table where the Q0 is the initial state and Q4 is the final state. So in the first step, we need to construct the pi naught. We need to construct some. I'll take here A, the caps A, that is equal to. Actually, the first set is nothing but the set of uh, final and non-final states. It is Q0, Q1, Q2, Q3. It is one set, and coming to another final set is Q4. Q4, it is our first set. Is our first set. Okay. Next step, we have to find the equivalence between the final states and non-final states. So now we need to find the equivalence between Q0 and Q1. The same manner, Q0 and Q2, Q0 and Q2. Here Q0 and Q3. So here, for all possibilities of Q0 Q1, Q0 Q2, Q0 Q3, we need to find. So for Q0 Q1, it is AB. It is AB. For Q1, it is Q1 Q3. It is Q1 Q3. Q1 Q3. Again for Q0 it is Q1 Q2. Q1 Q2. For Q it is Q1 Q2. It again. Okay. Here. For the third step, for Q3 value Q1 Q4, it is Q1 Q4. So we need to check the input A and input B for all three possibilities. Here the Q0 is in same state and Q2 Q3 is in same state. So Q0 is equal to Q1. Here Q1 in the same state, Q2 is in the one state. So again Q0 is equal to Q2 also. Q0 is equal to Q2 also. Here for Q1 same state and Q2 Q4 is the not state. So for this Q0 is not equal to Q3. So now next step is we need to divide A state to A1 in such a way that the equivalent parts in one set. So it is in one set it is Q0, Q1, Q2, and Q3 is another state and Q4 is another state. Q4 is another state. So it is A. So again we need to find the possibilities for Q0 Q1 and Q0 Q2. So Q0 Q1 and Q0 Q2. So again we need to check Q1. Here Q1 in the same state, Q2 Q3 is not same state. So Q0 is not equal to Q1, and here Q0 is equal to Q2. Q0 is equal to Q2. So by this next A So it is A1. So next A2, A2 is equal to A2 is equal to, it is Q naught comma Q naught is one state, and sorry, Q naught comma Q2 is one state, comma Q1 is one state, comma uh, Q3 is one state, and final Q4 is one state. So it is next value. So again we need to find Q naught Q2, Q naught Q2 for Q naught Q2 it is Q naught Q2. So here Q1 is in the same state and Q2 is also in the same state. Therefore Q naught is equal to Q2. So now A3 is equal to, now A3 is equal to, A3 is equal to A3 is equal to same as A2 because no not equivalence occur here. So if here A2 is equal to A3, so we'll stop the procedure here, and the number of states in the final automata is Q0, Q2, Q1, Q3, Q4. So the final automata is final automata is in place of Q0 we need to place Q2. Q2 in place of Q2 it is Q0, Q0, Q0. Here in place of we need to eliminate this state because it is equivalent to Q0 state, and Q3 here Q0 comma Q2. So it is the finite minimize the finite state machine for the given question, for the given this transition table. It is the final minimizer finite automata. Now we will draw the finite state machine for this. Okay. So the finite automata is the initial state is Q0, Q2. It is one state. So Q1 another state, Q3, Q4. Where Q4 is the final state, we need to represent with double circle. For Q0, Q1, if you give A, it is A. For Q0, Q2, if we give B, the output is B. And for Q1, if I give A, it is Q1 only. If I give B, it is Q3. For Q3, it is Q1. For A it is Q1, for B it is Q4, for A it is Q1, for B it is Q0, Q1. So it is the minimized finite automata. It is the minimized finite automata for the given problem. For the given problem here, so it is the answer for the given question. It is our answer for the given question. Okay. Okay. Next, we completed the conversion from NFA to DFA and minimized DFA also. Okay. Okay. Next, we'll start in regular expressions, regular language, in which it contains different types of operations on languages like union, concatenations, clean closure, and pause closure also. Okay. We'll see here, if the language L is equal, if you have two languages called uh, M and N, if you have two languages called L and M, if you perform the union operations, then L union M is equal to, it contains all strings that both in L and M. Okay, coming to concatenations, here concat is nothing but XY format where X is in the L and Y is in the M language. And next, coming to clean closure is nothing that is represented by operation is nothing but all possibilities along with null string here and so on L power I, where L power 0 is equal to with the length 0, L power 1 is equal to W with length 1, L power 2 is equal to W with length 2, and L power I is equal to W with length I. All combinations of the union of all L0, L1, L2 and Li is nothing but clean closure of the given language. The same manner, positive closure is also there. Positive closure is nothing but except L power 0, all L1, L2 and so on Li is comes under positive closure. Okay. Okay, now we need to go to next topic, conversion of RE to NFA with epsilon, regular expression to NFA with epsilon. Okay, In this basics, input is epsilon. For example, if your input is epsilon, it can be represented by the statement. It can be represented by the statement. Okay. If your input is A, then it is represented by using the diagram, the transition diagram, like this. If you have a string AB, then it is represented by A, it is AB. If you have A star, then it is represented by A. If it is A plus, then it is represented by A. These are the base and automata for regular expressions. For A star and A plus. Next, we'll go with A plus B. A plus B. So if it is A plus B, then the transition diagram can be represented by using NFA with epsilon, NFA with epsilon, it is the epsilon, 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 and epsilon. Here A and B. This is a representation of concatenation of two characters A and B. And one more, A star also can be represented by using epsilon. I'm writing here. There it is epsilon, A, epsilon, epsilon, epsilon. It is the representation. It is a representation of A star with epsilon transition or null transition. Okay. Now we will construct different types of finite automata with epsilon for the given regular expressions. So, example, if I enter A plus B into AB, I need to draw NFA with epsilon for the given regular expression. So for A plus B, we already know about the diagram. So it contains 6 states with epsilon. Without epsilon also we have one more possibility. I will draw later. So here epsilon, epsilon, A, B, epsilon, epsilon, and we need to add these two more characters here. So it is A, it is B. So it is the representation of A. Without epsilon transitions, we are also possible to draw directly from this regular expression. Okay, we'll draw now. So for it, if A plus B can be represented by using this without epsilon diagram, so it is NFA with epsilon. So it is A, B, it is A, B. Q3. Okay, this is the representation of NFA with epsilon and without epsilon also. With epsilon and without epsilon. So we'll see one more example here. One more example here. For that a plus b whole star, a plus b whole star, a plus b whole star. So for this actually we have an NFA without epsilon. It is a plus b whole star. So it is a. It is a plus b whole star. Okay, q naught q1. So if they ask NFA with epsilon, so it is represented by using. It is a very big diagram as compared with the before. So it is A, B, remaining all are epsilons. It is A plus B whole star. Then we need to add A also. Epsilon, 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 A, B, epsilon, epsilon. We need to add final state here. So epsilon, it is epsilon, and it is also epsilon. So it is NFA with epsilon. Here this diagram is NFA without epsilon. These two diagrams comes under the conversion of conversion of finite automata from regular expressions. So we have a direct procedure also. So now we will see the direct procedure for converting this NFA with RE to NFA without epsilon. RE regular expression to NFA without epsilon. So for the same question, a plus b whole star, a plus b whole star. This can be represented by using state. So here we have three strings, so we need to divide this into, so a plus b whole star, it is a plus b whole star. Okay. If the transition like this a plus b whole star, a star is nothing but it is a self loop. So we need to add the self loop to before transition. Sorry, after transitions it is a plus b whole star, a plus b whole star. Next a, and it is a plus b whole star, and the final diagram looks like, so it is a plus b. A plus b is nothing but a or b. So a, and finally it is also ab. So it is the final diagram for NFA, sorry, RE to NFA without epsilon, RE to NFA without epsilon. Okay. A few important points about this regular expressions. Regular expressions. Regular expressions. So now we will see some regular expressions. Here it is the diagram for 0 plus 1 whole star, 0 1, 0 plus 1 whole star. We already completed this NFA with RE to NFA with epsilon. Here we have some algebraic laws for regular expressions. It is we have a commutative law. Commutative law is nothing but if E and F are two languages, the concatenation of two languages E plus F is equal to F plus G. And coming to associative, E plus F plus G is equal to E plus F plus G. And so the regular expressions are associative under addition in concatenation along with multiplication also. Okay, annihilator is nothing but a pi value. It is a pi value. Okay. Coming to the properties of regular languages. Actually, we already learned about the regular languages that a language is said to be regular if it is accepted by the finite automata, whether it is a different deterministic finite automata or non-deterministic finite automata or NF with epsilon or regular expression. Then it is said to be regular languages. If we are not able to build any finite automata, then the language is not said to be regular language. Okay. Okay. One shortcut for whether we have to find the given language is regular or not is if any condition is there in the language, then the language is said to be not regular language. Condition is nothing but for example, L is equal to A power n, B power n. Here L is equal to A power n, B power n means here L is equal to A power n, B power n means here number of A's is equal to number of B's. We have a one comparison here. For every A, we need to compare, we need to check whether there is a sufficient B in the given language. Otherwise, we don't want to construct regular languages for this type of languages. So if there is a condition between two variables, then we are not able to construct that finite automata for the given languages. So L is equal to A power n. L is equal to A power n is a regular language because we will construct the finite automata for the language L is equal to A power n. Okay, but L is equal to A power n, B power n, and another language L is equal to A power n, B, A, C, A power n. So this type of languages have some dependency on the remaining part of a string. So we are not able to perform, we are not able to construct finite automata for such type of languages. Then these languages are not said to be not regular languages. Okay. And coming to pumping lemma of regular languages, the pumping lemma theorem is useful to check whether the given language is not regular or not. Not regular or not. Okay. Not regular or not. For example, if I take the language, L is equal to A power n, L is equal to A power n, B power n, where n greater than or equal to 1. If this is the language, we have the language as AB, comma, AABB, comma, triple A, triple B, comma, 4A's, 4B's, comma, and so on. If I take one string here, triple A, triple B, is belongs to given language, is belong to given language. So we will divide the given string into W is equal to XYZ. W is equal to XYZ in such a way that X is equal to A, X is equal to double A, next Y is equal to AB, and Z is equal to BB. So if XYZ is belongs to the language, then x y power n z is also belongs to the same language. Is also belongs to the same language. Is also belongs to the same language. Then the language is said to be regular language. Here W is equal to AABB, sorry, AAABBB. This is the language. So if x y power square x y square z is equal to, which is AB, it is not belongs to the language. So the language L is equal to A power n, B power n, where n greater than or equal to 1 is not regular language by using pumping lemma theorem. So here the main point is, for the given language L is equal to A power n, B power n, we need to construct the language first. Already we constructed here L is equal to AB, AABB, and AAA, 4A, 4B also. Okay, in that we will pick one string, whether it is AB or AABB or AAA, BBB, or whatever you require. So I'll take here a AAA, BBB, X is equal, sorry, W is equal to AAA, BBB. I need to divide the given string into XYZ format. Whatever the partition it is, we need to divide the given string into XYZ format. I will take X is equal to AA, Y is equal to AB, and Z is equal to BB. If XYZ belongs to given language, then X into Y power n Z is also belongs to the given language. Then it is said to be the language is regular. The language is regular. For example, if you take one more language, L is equal to A power n, where n greater than or equal to 1, where n greater than or equal to 1, n greater than or equal to 1. So we need to construct the language L is equal to A comma double A comma triple A comma 4 years comma and so on 5 years and so on. Okay, now we'll take one string. So it is 4 star. Sorry, it is 3 stars. So W is equal to 3 years. So I need to divide the given string into 3, right? X is equal to A, Y is equal to A, some Z is equal to A. So if XYZ belongs to given language L, X y power n Z is also belongs to the given language. So X y square y cube x y power 3 Z is equal to, here A y power 3 means triple A and A. So it is 5 years. So here 5 years is belongs to the given language. Here given language L. So is belongs to given language L. So it is regular language based on pumping lemma theorem. The above language is not regular because the X y power I Z is not belongs to given language L. Okay. Okay, this is about the regular languages, conversion of NFA from regular expression, and minimized DFA, and pumping lemma theorem. And pumping lemma theorem. Here the example, we have, so here 0 power n, we have 0 power n, 1 0 power n, where n greater than or equal to 1 is also not regular, because here we have a condition before 1 and after 1. So the number of zeros before 1 is equal to number of zeros after 1. We have a condition, then the language L is equal to 0 power n. 1 0 power n is not regular language. Based on pumping lemma is also, it is not. Here also 0 power I, where I is a perfect square. So here also we have a condition where I is a perfect square. If any language have a condition like this, is not regular language, because the finite automata does not contain any memory, any arbitrary memory to store or to check whether the given conditions are satisfied or not. So it is not regular. It is not regular. And finally, coming to the closure properties of regular languages, the regular languages are closed under. If the closed under means the union of two regular languages is regular. The intersection of two regular languages is regular. The complement of a regular language is regular. In the same manner, the regular languages satisfy all the properties listed here. The union, intersection, complement, difference, reversal, clean closure, concatenation, homomorphism, and inverse homomorphism also. Okay, so it means that the regular languages are closed under union, the regular languages are closed under intersection, the regular language closed under complement, difference, reversal. For example, if two languages A and B are regular, then A union B is also regular language. In the same manner, if two languages A and B are regular, the A intersection B is also regular. Okay, this comes under regular languages. For your GET exam, there is no need to learn about the proofs of this regular closure properties of regular languages. Okay.